Okay, so now let's look at what happens when you have a tensor product of operators or gates, right? So here's what I mean. So let's say you have two qubits and you apply a quantum gate U to the first qubit and V to the second qubit. So now what we want to know is what's the unitary transformation we've applied to the two qubits together, right? So in other words, what we want to know is if U was A, B, C, D and V was E, F, G, H, then what's this transformation we've applied to the two qubits? Well, the way we denote it is we denote this transformation by U tensor V. And it's going to be a 4 by 4 matrix, right? Indexed by 0, 0, 0, 1, 1, 0, 1, 1. And what it'll look like is so these first four entries will look just like V, except they'll be scaled by A. These four entries will look like V, except scaled by B, and so on. Okay, so here's what I mean by this. So let's write out these first four entries explicitly. So these first four entries would be A times E, A times F, A times G, A times H. Okay, so let's try to understand why this is the case. So first of all, let's just make sure we are on the same page with respect to convention. So if you were to, if we were to say the input is 0, 1, right? What does that mean? Well, it means that this qubit is 0 and this qubit is 1, right? Okay, so now let's try to understand what happens if we apply U to this qubit. Well, what's that doing? Well, so remember, it's only applying it to this first qubit and leaving the second one unchanged. And so since it leaves it unchanged, it's as though, sorry, it applies it only to this first qubit and leaves the second one unchanged, right? So what are we doing when we leave the second one unchanged? It means that we go from 0 to 0 with amplitude A, right? So it's as though all these four entries, whatever happens to them as a result of the second gate, what the first gate does is it goes from here to this quadrant with amplitude A. And similarly, this quadrant has amplitude B, C, and D. Right? That's the effect of U. The effect of V, okay, so if you were to write down the effect of V, well then what happens there? Well, now V is acting on this qubit, which is in the least significant position. So okay, which means that you're going from 0 to 0 with amplitude E, F, G, H, right? And then, of course, it has to be scaled by whatever amplitude you go from, the most significant bits stays as 0. Okay, so if you put both of these effects together, what you get is that the transformation is exactly this. you get each of these 2 by 2 blocks is a scaled version of V, the transformation V. And what scaled version? Well, depends upon which quadrant you are in. It's either scaled by A, B, C, or D. It's exactly in the pattern according to you. Okay, so let's do an example. So suppose now U was equal to the Hadamard transform and V was equal to X, which is 0, 1, 1, 0. Okay, so now, and H, of course, you know, is 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2. So what is H tensor V equal to? Well, so what do we get? Well, we'd get 1 over square root 2 x, 1 over square root 2 x, 1 over square root 2 x, minus 1 over square root 2 x, which if you open this out, it's 0, 0, 1 over square root 2, 1 over square root 2, 0, 0, 1 over square root 2, 1 over square root 2, 0, 0, 1 over square root 2, 1 over square root 2, and 0, 0, minus 1 over square root 2, minus 1 over square root 2. Right, so we just took multiples of x here as each of these 4 blocks.